afternoon, sir.
Okay, let us start this lecture. In the last lecture, I don't know how many of you were present that time, but in the last lecture, I am audible to everyone.
Yes, sir.
Yes, sir.
Yes, sir.
So, in the last lecture, we have seen the basics of queuing model, and we have seen that it is also called as waiting line problem or model, and we have seen the basics of the queuing models. And most importantly, after that, we focused on four basic models of the queuing model, and we have seen the first model, that was a model having a Poisson's arrival, exponential departure, single server, infinite capacity model, infinite population model, and the discipline was first come, first serve. That model we have seen. Problems based on that model, that also we have seen. Now today, we'd like to discuss the model 2 and model 3. Basically, these four models, they are broadly classified as single server models and multiple server models that we have seen. In single server model, we have seen that the server or facility is only one, irrespective of the arrivals. Whereas in multi-server model, we are having more than one server or facilitator. That we have seen, that you know very well. Now let us move to model number 2. You can see model number 2 by using the Kendall's notation. We have written it as M/M/1 N oblique first come first serve. The meaning of this model is that, or the significance of this model is that the arrival pattern is Poisson, the departure pattern is exponential departure pattern rather than service pattern. It is exponential service time. The server is still single server, but the change as compared to the first model is that here you can see the change in this model. Earlier in the first model, we used to have infinite population, but now we made it a finite population now. The population is finite now. And the discipline, it remains same. Discipline is same, that is first come, first serve. So this model, in this particular model, we are having a waiting system or queuing model where the server is only one. The arrivals, they are following a Poisson distribution. The service pattern is exponential. So, and only one server is there, single server is there. But then queue length is finite. The meaning is that the number of arrivals reaching that particular server has a limit. They are finite. They are not infinite as we have seen in the first model. And the discipline is first come, first serve discipline. Now, I will like to elaborate this change of finite queue length as compared to infinite queue length that we have seen in the first model. Again, I will like to cite the example of a doctor who is working in his own clinic. Doctor is only one server, is a single doctor in that clinic, and he is serving the patients. In earlier case, we have seen that this clinic was open for all patients, and that too for infinite number of patients. But the second model says that the doctor has considered some limitation, and he has decided to select treat only finite number of patients. For example, any doctor who reaches that particular clinic and he decides that he will attend only 50 patients. If you put that limitation, then the model becomes finite queue length model. And this model too is finite queue length model. And n is indicating a finite number here. That's all. Now let us see some assumptions and salient features of this particular model. The model, in this case, you can see the model. There is only one queue and only one server. One queue and one server. Then the model is applicable when queue can accommodate a limited number of customers. So this is specifically, the model is specifically for limited number of customers. That is, the maximum number of customers in the system is limited to n. So what is the meaning of that? If we decide the value of n is equals to 50, the doctor will not allow the 51 patient to enter into the clinic. So he has restricted his number of patients equals to 50. So it's a limited model. Now what happens after 50? If new arrivals joins the queue, they are not allowed to enter the system. And this is a special example of bulking. You have seen this particular term bulking, and I have explained the term bulking. It is the term which indicates that the new arrivals are not allowed to come into the system, or in other words, I can say that new arrivals do not join the system simply because the capacity of the system is restricted or capacity of the system is full. So restrictions are normally done on that particular system where it has got some constraint. One can understand that one doctor, a single doctor, can treat 50 patients effectively, but if someone asks him to treat 100 patients, then his efficiency may go down, his performance may not be to the mark, and in that case, one has to put some restrictions because of the capability of the system or capacity of the system. So, bulking, this term refers that it is basically used in model 2, where the capacity is restricted. Then in this particular case, in this particular model, the arrivals, they are considered completely random. They are not following a specific rule. They are randomly coming. For example, if a doctor decided to start his clinic by 10 a.m. and he will continue it up to 6 p.m. and even if he decided that the number of patients that he is going to attend is 50, and imagine that instead of 10, some patients or the first patient reaches the clinic by 11, so doctor will have to serve the 50 patients and he may extend his limitation or his timing from 6 p.m. to 7 p.m. That may happen. But in this case, we assume that doctor is going to attend 50 patients irrespective of the pattern in which they are arriving in that particular system. So arrival is completely random. It is considered completely random, but it follows a Poisson distribution. Then the time interval between the consecutive arrivals, time interval between two successive arrivals, as well as consecutive services, it follows a negative exponential distribution. Remember that it follows a negative exponential distribution. So this is about, these are the salient features of this particular model. And in queuing models or waiting line models, the basic concepts regarding all these models that we have almost discussed. in the first lecture. Now here we are going to see the measures of this model. Measures of this model means these are the performance check of this model. For example, the first performance check of this model. Everybody knows that lambda, we denote it, lambda, it is representing the arrival pattern of the customers. Mu is the service rate. Then N, capital N, it is indicating the capacity of the system. In this case, in the case of this doctor-patient clinic, this model, the capacity is, for example, 50. So N is indicating 50, capital N. So now first check, probability of 0 customers in the queue system. The first check says that what is the probability that there are 0 customer in the queue system. This indicates that there is no customer in the system. In other words, we can say that this particular system is empty system. The queue is empty, the system is empty, and hence that emptiness we can calculate by P0 is equals to 1 minus lambda by mu divided by 1 minus lambda by mu to the power n plus 1. It is n plus 1. Remember that it is n plus 1. So in this case, you can convert this formula in terms of traffic intensity also, because we know that traffic intensity, it is always equal to lambda by mu. So instead of this ratio lambda by mu, sometimes rho is kept over there, because rho is the ratio of lambda by mu. So we can write this example as 1 minus rho upon 1 minus rho to the power n plus 1. So that way we can also write the formula. All of you getting this thing? Are yes or no?
Yes, sir.
Okay. Now next measure of this model is probability of n customers in the queue system. The meaning is that if you want to find out the exact number of customers in the system, the exact number of customers in the system by that particular time we cannot find, but probability of n equals to 27 in that particular queue system, that can be found, and it is given by Pn equals to lambda by mu to the power n multiplied by P0. So Pn is equals to lambda by mu to the power n multiplied by P0. It gives us the probability of n customers in the queue system. Then we'll go for the next measure of this model. If someone wants to find out the average number of customers, average number of patients visiting to that doctor, or visiting that doctor and they are waiting for the doctor, in that case, average number of customers in the queue, they are given by LQ, n is equals to 1 to n is equals to capital N. Now here in this case, you can see that small n and capital N, there is a difference between capital N and small n. Small n is indicating the number of patients in the clinic, in the queue, whereas capital N is indicating the capacity of the clinic. So in this particular example, we have decided the capacity of the system n equals to 50, and n small n, it may range from 1 to 50. It may range from, even we can count 0 to 50. So small n, it may be from 0 to 50, whereas capital N indicates the capacity of that particular system, which is 50. Now next measure of the system is average number of customers in the queue system. Average number of customers in the queue system. Now you can see the difference between the average number of customers in the queue and average number of customers in the queue system. It is quite clear that every system, if you consider a system, the total number of customers in that system is always equal to number of customers in the queue plus one, that is the person or the customer who is getting a service. Because it is a single server model, it indicates that only one customer will get a service and the rest of the customers they will wait. So total number of customers, if you want to find out for that particular system, it is always equals to one customer who is getting service plus the customers who are in the queue. So you can see the change here. When we find out the average number of customers in the queue system, the formula is more or less same. In earlier formula, that is the average number of customers in the queue, we are considering n minus 1. Why minus 1? Because this one number or this customer, this patient is getting the service. So n minus 1 number of patients, they are in the queue. One is getting the service, and that's why total number of customers will be n minus 1 plus 1. That means it is equals to n. Hence, average number of customers in the queue system is equals to n. Next, another measure of this model is average time a customer spends in the system. Here we want to find out the average time a customer spends in the system. So that is the meaning is that the customer is reaching to that particular place. He is in the queue. He is giving some time in the queue, and after that he is getting this service. So total time expected by the customer in the system is equals to the time he spends in waiting, that is in the queue, plus the service time. That's why average time a customer spends in the system, it is equals to LS, length of system divided by lambda. Whereas average time a customer spends in the queue, that means the case where we are not considering the time spent for getting the service. So that is given by WQ is equals to LQ upon lambda. Here note I have given, I have already explained you that if you want to simplify all these formulas, you can put just sigma, that is you can put rho, that is traffic intensity, which is equals to lambda by mu. So you can change all these formulas by substituting rho instead of ratio of lambda by mu. So these are the 6 basic measures of model. That means these 6 formulas we can use to check the features of this particular model. I expect you to practice at least 10 problems for a particular model. And for that, I feel that you should refer the last 5 years question paper. And if you solve all those problems, it will be more than sufficient. So let us discuss this particular problem now. Now in this case, a local one-person barber shop. You have to concentrate on the wordings of the example problem. Here, the moment we say one-person barber shop, that means it is a single server problem. Because in examination, you will have to differentiate. You will have to find out the problem to which model it belongs, and it is quite clear that if we say one-person barber, that means it has got only one channel. It is a single server problem. Next, once you identify it is a single server problem, next task is to identify whether it is infinite, it is having infinite population or it is having finite population. So one single person has a space to accommodate 4 customers. Now here it is quite clearly mentioned 4 customers. The system can accommodate 4 customers. The meaning is that it is a finite queue length or finite population model. So it is a second model, single server and queue length is only 4. So here the value of n, capital N, is equals to 4, and the value of C is equals to 1. So a local one-person barber shop has a space to accommodate 4 customers, 3 of them waiting and 1 being attended at a time. If a customer comes to his shop and finds it full, he goes to the next shop. Customers arrive at random at an average rate of 4 per hour. So this is the arrival rate, lambda, arrival rate of the customer. Customers arrive at random at an average rate of 4 person per hour. So lambda is equals to 4 per hour. So it is 1 by 4. Now next, and the barber's service time is negative exponential with an average of 10 minutes. It is negative exponential with an average of 10 minutes. So it is service rate. So one person being served in 10 minutes. So mu is equals to 1 by 10 minutes. Now if lambda and mu, they have different units, you need to convert them. You need to make them of same units. So either convert this 4 per hour into minutes, or this 10 minutes, 1 per 10 minutes into hours. Both the things are possible. Now here we have to determine the probability distribution for the number of customers waiting for service. To determine the probability distribution for the number of customers waiting for service. Then second is, what is the probability that a customer can get the service directly on arrival without waiting? That is what you can say that this will happen only when the system is empty, right? If one is not required to wait and he is getting service directly, this indicates that the system is empty. So you will have to choose those 6 formulas and apply here and answer these questions. Now next one, what is the expected number of customers waiting in the barber shop? That we have to see. Then what is the expected number of customers in the barber shop? How much time a customer expect to spend in the barber shop? So we'll answer all these questions one by one. But before that, we'll try to understand the meaning of these questions. Let us consider the first one. Now here, since it is a model number 2, single server model, population is finite. So here we will have to write n is equals to 4 because it is given. Because it is given that capacity of that barber shop is 4. 3 may enter into the barber shop. That means they may wait when one of them they are getting service. They are getting the service. Now here n is equals to 4. Arrival rate is 4 per hour. So you may convert this 4 per hour into minutes, or you may keep it. And in that case, you will be required to convert the mu into from minutes to hours. So arrival rate is 4 per hour, whereas service rate, which was 1 by 10 minutes, now we have converted it into hours. So it becomes 6 per hour. And the ratio of lambda by mu is 4 upon 6, that is 2 by 3. So we'll use lambda by mu equals to 2 by 3, which is equals to rho, that is traffic intensity of this particular system. Now let us answer the first question. The first question is, determine the probability distribution for the number of customers waiting for service. The probability distribution for the number of customers waiting for the service. This indicates the probability distribution or the number of customers who are present in the system. So it is given by Pn, which is equals to lambda by mu to the power n into P0. So first thing is that for finding the value of Pn, we will require to find out the value of P0. And what is that P0? P0 is probability of 0 customers in the queue system. So when you want to find out P0, its formula is 1 minus lambda by mu upon 1 minus lambda by mu to the power n plus 1. And this value of P0, it comes out to be 0.3838 when you substitute the value of lambda by mu equals to 2 by 3. Now in this case, For our convenience, always try to find out the value of number of customers present in the system. Since the total number of possible customers in this particular system ranges to 4 only, that means we will be required to find out the value of P0, P1, P2, P3, P4. And its formula is known to you. For finding the value of P0, it is lambda by mu to the power n into P0. So P0, anything to the power 0, anything 0 to anything, uh, 0 is the power here. So lambda by mu to the power 0, it is equals to 1 multiplied by P0, it's 0.3838. So P0 is equals to 0.3838. P1 likewise lambda by mu to the power 1, n is equals to 1 into P0, its value is 0.2558. Likewise, we will find out the value of P2, P3 and P4, which are respectively 0.1705, 0.1137, 0.0758. Now, next thing is to find out. Here we have already calculated now the value of Pn, where Pn is indicating the probability distribution for the number of customers in the shop. If you want to find out what is the probability of number of customers 0 in this particular shop, that probability is 0.388. Likewise, if you want to find out the probability of 4 customers in the shop, that probability is 0.0758. Right? We have answered this particular question. The second question is, what is the probability that a customer can get the service directly on arrival without waiting? So I have that this indicates that the probability that a customer gets the service on arrival without waiting, that means system is empty. There is no customer in the barber shop. That's why the moment anybody enters into the system, you will get the service. So we are talking about empty queue or 0 customer in the queue system. And that we have already calculated P0, which is 0.3838. So answer to this question is the probability that a customer gets the service on arrival without waiting is 0.3838. Next question is, what is the expected number of customers waiting in the barber shop? We have to find out the expected number of customers waiting in the barber shop. That means we are talking about the customers who are waiting only. Those customers who are waiting only. And waiting means we want to find out the queue length. So LQ, for that, the formula is known to us. LQ, it is equals to summation of all n equals to 1 to n equals to n. It is n minus 1 into Pn. Let's see how to calculate that. Since it is a summation, it will be 0 into P1 plus 1 into P2 plus 2 into P3 plus 3 into P4. Anybody is having any difficulty here in understanding this last step?
Sir, can you please repeat the LQ?
Again, LQ is the number of customers who are in the queue. LQ indicates number of customers who are in the queue. So how many number of customers there will be in the queue? There will be total number of customers in the system minus 1. Why minus 1? Because out of these n, one of them will be attending, will be getting service. So number of persons who will be in queue, it will be n minus 1 into Pn. Right? Now the value of n, in this case, the value of n, that is capital N, that is the capacity shop, capacity of the barber shop. It is how much? 4 only, right? It is 4. So when you will calculate LQ, will substitute initially when n is equals to 1. If you put the value of n is equals to 1, what will happen? N is equals to 1 means 1 minus 1, it will become 0. 1 minus 1 will be 0. Here you can see that 0 into P1 it will be ultimately 0. When you are considering two customers, it will n minus 1 means 2 minus 1, that is 1 into P2. Likewise, plus 2 P3 plus 3 P4, since it is the summation. So this you will calculate. 0 into P1 is obviously 0. 1 into P2 means 1 into P2. What is the value of P2? P2 is 0.1705. So 1 into 0.1705 is again 0.1705. So this way we'll calculate the value of LQ. Is there any difficulty?
No, sir.
Is there any
It's good.
difficulty? और आगे बढ़ना है अभी?
Yes, sir.
Yes, sir.
Next is to find out the expected number of customers in the barber shop. When I say that, what is the probability or what is the expected number of customers in the barber shop? The meaning is that we have to find out the number of customers who are waiting in the queue plus getting service. So it becomes a system, right? So for that, we are using the formula LS is equals to N equals to 0 to N equals to N. It is N into Pn. Since it is a summation, we can write it as 0 into P0 plus 1 into P1 plus 2 into P2 plus 3 into P3 plus 4 into P4. The values of P0, P1, P2, P3, P4 we have already calculated in the last chart. You're just supposed to put these values and finally you will get the number of customers in the shop, expected number of customers in the shop, which comes out to be 1.2411. And the last one is the time customer expects to spend in the shop. So here you have to decide whether it is WQ or WS. Again, whether it is the time spent by the customer in queue only or whether the time spent by the customer in the system only, right? When I say that, how much time can a customer expect to spend in the barber shop? Barber shop is a system. That's why we have to consider it as a WS. That is the waiting, that is the time spent by the customer in the barber shop, which includes waiting time plus the service time. It is equals to LS upon. So it is 18.61 minutes. So this way, you will have to solve the problem. You will have to focus on only these 6 measures of this particular model, and considering the nature of the questions, you will have to analyze them, whether they fall in the category of LQ, LS, WS, WQ, P0, PN. You will have to identify that and then you will have to solve. Now let us consider the second problem, one more problem. This problem is, it says that trains arrival or arrives at the yard every 12 minutes. So arrival rate at which the trains arrive is 1 by 12 minutes. Lambda is equals to 1 by 12. And the service time is 35 minutes. That means the rate at which these trains are getting the service, it is 1 by 35 minutes. So mu is equals to 1 by 35 minutes. If the capacity of the yard is limited to 4 trains, fine. Number 1, probability that the yard is empty means you will have to find out P0, the average number of trains in the system and the average number of trains in the, very simple. When I say that it is yard, that means it is a single server. When I say that only 4 trains are allowed to come into the yard, that means it is a finite. It is having a finite capacity. So n is equals to 4 here. So we will use the second model and we will use the measures of the second model. Here you can see that lambda is 1 by 12 minutes. So we have converted this into R. by multiplying it by 60. Mu is equals to again 1 by 35. So we have converted it into hours by multiplying 60. So these are in terms of hours now. We can find out the rho, that is the traffic intensity, which is lambda by mu. So it is equals to 2.916. Now the first question is to find out the probability that the yard is empty. When I say that the probability that the yard is empty, that means we will have to use the first formula. That means there is no customer in the yard, no train in the yard, and which is given by this formula P0 equals to 1 minus lambda by mu upon 1 minus lambda by mu to the power n plus 1. So everything is known to us here. Lambda, value of lambda, mu, n is known. We have to just substitute this value and we'll get the answer. Now, if I want to find out specifically the number of trains, possible number of trains in that particular yard, then it becomes Pn equals to lambda by mu to the power n into P0, right? P0 already calculated. So just substitute the value of P0 in this equation. You will now. Second question is to find out the average trains in the system. So for that again, the same, we will use this formula, which gives us the number of trains in that particular yard. That means number of customers which are visiting in that particular system. The possible number of customers visiting that yard is n is equals to 0 to 4. There may be 0 train, there may be 4 trains. Because maximum number of trains that are allowed to enter into the system, they are given equals to 4. And it is n into Pn. So applying this formula, it will be 0 into P0 plus 1 into P1 plus 2 into P2 plus 3 into P3 plus 4 into P4. Just substitute the value of lambda by mu here and you will get the average number of trains in the system. Last is to find out the average number of trains in the queue. So again, since it is a single server model, the yard, it can serve only one train at a time. It will repair, maintain only one train in the yard. The rest of the trains will have to wait. So average number of trains in the queue, that we can calculate by using LQ formula. Similarly, you will have to just put the values and you will have to find out the answer, that is 2.51. So this way, you will have to solve the problems which are based on this particular model. That is a model having single server and finite number of customers. Let us move to another model. Next. Now till this time, we have seen all the models which were having a single server, Consider a single server with infinite population as well as finite population. Because the first model, it was single server model with infinite population, and the second model which we have seen today, it was single server model with finite population n. But model number 3 and 4, they fall into the category of multi-channel, multi-server models. Now in this case, let us analyze the significance of this MMC infinity FCFS. The significance is again, the customers arrive at Poisson arrival. They depart or they get the service in an exponential manner. The number of servers, they are multiple. That means the number of servers, they are more than one. C is always equals to more than one. The queue length is infinite queue length. If you consider the same example of the doctor who is sitting in the cabin, it will not work here. Now, instead of that, you may consider that there are more than one doctor in that particular hospital and they are waiting for infinite number of customers. Or the other example, the best example is a railway reservation counter, where we can have more than one servers working, and more than one window, and the queue length is also infinite. Infinite means unlimited number of population, unlimited number of customers can come to that particular reservation counter. And in all the cases, you will see that the discipline which is maintained is first come, first service rule, because it's a natural rule. That's why in all these models, you will see that the first come, first serve type of model discipline is considered. So I hope it is clear to you. The only change in this particular model as compared to the earlier models is that instead of single server model, now it is a multi-server model. We are considering a railway reservation counter where the number of windows, they are more than one. It may be 2, 3, 4, and C. Let us see the measures of this model, and before that, let us consider the assumptions. There are several in the service facility and are arranged in parallel. Particular system, it consists of several servers who are arranged in parallel. Second, the customers wait in a single queue, but the queue is single. Queue is always single. Queue until any one of the servers becomes free to render the service. Third one, the arrival rate is lambda and the service rate is mu. And these lambda and mu are mean values and they follow Poisson distribution and exponential distribution respectively. The service rate is same for each server. Service rate is same for each server. It is not like that one server is working very fast. That means out of those C, one is working very fast and the other one is working slow. It is not like that. All the servers, they are working at the same rate. The next one is the average arrival rate is less. Average arrival rate of the customers is less than the combined average service rate of all servers. Combined average service rate of all servers. That way we can say that the service rate is same for each server. We are finding the average service rate of all the servers. And it is expected that arrival rate is always less than the average service rate of all servers. Then the queue is of infinite length. This is the case we have seen, infinite population. Now let us see the measures of this model. Here you will have to remember around 30 to 32 formulas. If you consider all the four models, you will have to, if you combine all these formulae, you will have to remember at least 30 to 32 formulas. There is no derivation in our syllabus. Only thing is that you will have to remember the formulae, because you can see that the probability that there is no customer in the system, P0, it was different in the first models, it was different in the second, and it is different in this particular third model also, right? So how to find out the probability that there is no customer in the system? P0 is equals to summation of n equals to 0 to n equals to c minus 1. Here n indicates the possible number of customers in the system, and c indicates the number of channels, number of servers in the system. And this probability that there is no customer in the system, it is given by this formula, summation n equals to 0 to n equals to c minus 1, 1 upon factorial n into lambda by mu to the power n plus 1 upon factorial c into lambda by mu to the power factorial c multiplied by c into mu upon c into mu minus lambda to the power minus 1. Or else we can write this formula as 1 divided by this as denominator. This is the value of P0. That is the probability that there is no customer in the system. Second measure of the model is probability that there are n customers in the system. Probability that there are n customers in the system. It is given by lambda by mu to the power n into P0. And here the number of customers, the value of n, it is always less than c. The next, average number of customers in the queue. Average number of customers in the queue, it is given by lambda into lambda by mu to the power c upon c minus 1 factorial into c into mu minus lambda whole square into p0. Likewise, fourth measure of this model, average number of customers in the system. Now in this case, remember that once you remember the formula for LQ, the next formula for LS, you will have to remember, I will suggest you to remember this particular formula. Because if you know the formula of LQ, straight away LS is equals to LQ plus lambda by mu. It is easy to remember. That's why remember this particular formula. But actual formula is this one. This is nothing but the LQ value plus lambda by mu. The next, average waiting time in the queue. Once you know LQ, you can find out WQ, that is LQ by lambda. Similarly, if you want to find out the average waiting time in the system, it is WS is equals to LS by lambda. So, simple way to remember 1, 2, 3, and earlier 4, these four formulas is to remember the formula for LQ. Once you know the formula for LQ, you can find out LS, you can find out WQ, that is LQ by lambda, you can find out WS, that is LS by lambda. This is the way you can remember these formulas because they are really difficult to remember. The next one is utilization rate, that is traffic intensity. Traffic intensity, for single server we have seen that the traffic intensity is lambda by mu. Here the servers are C, they are not 1, they are C. That's why there is a change in the value of rho, that is lambda divided by number of servers multiplied by mu. Then next, probability that a customer has to wait. What is the probability that a certain customer will have to wait? It is new particular model. It is probability that these number of customers will have to wait when the channels are C, it is equals to mu into lambda by mu to the power C divided by C minus 1 factorial into C mu minus lambda into P0. And the last measure is probability that a customer enters the service without waiting. That means this is again a case where the system is empty. All the servers, they are empty. In that case, we will have to find it 1 minus probability that there are these many number of customers. Right? Once you find out this value from this formula, you will be able to find out the probability of no customer in the system. So these are the 9 measures of this particular model. Let us see the example based on this model. Again, I have considered 2 examples. Let us see the first example. Here, Sunil Medicals is manned by 3 salesmen. Sunil Medicals is manned by 3 salesmen. Now, in earlier case, we have seen that the number of salesmen, it was 1. Number of doctor present, it was 1 because it was single server model. Now it is a multiple server model. So the change, you can see that there are 3 salesmen. This is the indication to identify that this model is at least a multiple server model. So first thing is to find out whether the model is a single server model or a multiple server model. So you will have to focus on this question. The wordings here, 3 salesmen indicates that it is a multiple server model. Now next question is to find out whether it is an infinite population model or finite population model. Now let us see. Any salesman can provide desired service to any customer. The customer arrive at the counter according to portion distribution at an average rate of 30 per hour. 30 per hour. The service time is exponential with a mean rate of 3 minutes. And the service time is exponential with a mean rate of 3 minutes. Now, what fraction of time are all 3 attendants busy? Second question, what is the mean number of customers waiting to be attended? what average time does a customer spend at the shop? And last one is, what is the probability that a customer has to wait? Now, from the given problem, C is equals to 3, it is indicating number of salesmen. Then lambda is equals to 30 per hour, mu is equals to 60 by 3. This is because the service time is exponential with a mean rate of 3 minutes. So it is mu is actually equals to 1 by 3. So this becomes 1 by 3 multiplied by 60, so 20 per hour. And lambda by mu is 30 by 20, that means 3 by 2. So first question is, what fraction of time are all the 3 attendants busy? So we have to find out the utilization factor. How many, what is the, how much time they are busy, all 3 attendants. That means we are finding the utilization factor of the system. And when we say utilization factor, that means it is the traffic intensity. Traffic intensity is rho, which is lambda upon C into mu for multiple server models. Just substitute the value of lambda, that is 30, value of 20, value of C is equals to 3. So you'll get the traffic intensity, utilization factor. Second one is, what is the mean number of customers waiting to be attended? Mean number of customers waiting to be attended. Mean number of customers waiting to be attended. That means the number of customers who are in the queue. That means the average number of customers in the queue, which is given by LQ. Formula for LQ is known to us. This is the formula for that, multiplied by P0. So first thing is that the value of lambda is known, mu is known, C is known. Now we will have to find out the value of P0. How to find out the value of P0? That is also known to us. P0 is equals to 1 upon summation of n is equals to 0 to n is equals to C minus 1, lambda by mu to the power n upon factorial n plus lambda by mu to the power factorial C, is C into mu upon C mu minus lambda. So you will have to put the values of lambda, C, mu, and finally you will get answer that you will work out. You will work out at home how to find out the value of P0. It is very simple, right? Then after that, we will find out the average number of customers in the queue. To find out the average number of customers in the queue, we have already discussed the formula. That was this multiplied by P0. So once you get the value of P0, which is 0.21 here, what you will do? You will substitute the values of lambda, mu, and C in this equation. Multiplied by P0 means 4 by 19, which will give you the value of LQ. That is the average number of customers in the queue. That is 7.1053. Then next is to find out the average time a customer spends in the shop. Average time a customer spends in the shop means in the system. When you want to find out the average time a customer spends in the system, that is WS, it is LS upon lambda. But for that purpose, you will have to find out LS. And how to find out LS? LS is equals to LQ plus lambda by mu. So find out LS first. So we'll find out the length of the system. Length of the system is equals to LQ 135 by 19 plus lambda by mu, that is 30 by 20. So it will be 96 by 19. Then WS is equals to LS upon lambda, that is 96 by 19 divided by lambda, or multiplied by 1 by 30, because lambda was 30 that time. So this time a customer spends in the system, that is 0.1684. The next question is, what is the average waiting time for a customer? Waiting time for a customer, WQ, it is LQ by lambda. LQ is known to us, lambda is known to us, you will get this value. The next question is, probability a customer has to wait. Probability a customer has to wait. That probability is given, again the formula is known to us, just you will have to put the values of mu, lambda, and C, that's all. you will get a probability a customer will have to wait in that particular system. Let us consider one more problem. The problem is a supermarket has two sales girls. Two sales girls. It is not only one girl. That means it is a multiple channel, multiple server system. A supermarket has two sales girls at the sales counter. If this service time for each customer is exponential with a mean of 4 minutes, means service rate is given 4 minutes, 1 by 4, one person in 4 minutes, mu is equals to one person in 4 minutes. And if the people arrive in fashion at the rate of 1 in at the rate of 10 an hour, 10 an hour, calculate probability that there is no customer in the system. System is empty. Average number of customers in the queue, that is LQ. Average number of customers in the system, that is LS. Average waiting time in the queue, that is WQ. And utilization factor, that is traffic intensity, which is rho, which is equals to lambda upon C into mu for a multi-server model. So again here, considering these values of lambda, mu and C, we'll find out the probability that there is no customer in the system, which is equals to P0 is equals to 1 upon this particular factor. Again, substitute the value, you will get the answer, P0. Average number of customers in the queue, LQ, is equals to this factor multiplied by P0. Value of P0 is known, you will calculate LQ. Average number of customers in the system, LS, it is equals to LQ plus lambda by mu. You will get the value. Average waiting time in the queue, WQ, it will be LQ upon lambda. You will get the value. And finally, utilization factor, rho, that is lambda upon C into mu. So it is 1 by 3. So basically, if you analyze this waiting line theory or queuing models, you will realize that more important is the basic concept. Once you know the basic concepts of queuing models, once you remember all the measures of these 4 models, solving problem is very easy, right? But then you will have to remember the formulas for all these 4 models and you can easily solve them. So with this, we have completed the model number 2 and model number 3. Now about model number 4, that we will see on another day. We'll conduct one more lecture, and with that we'll be able to finish waiting line theory. So I hope Professor Barve, he has already completed, I think, which topic he has completed? Which topic he has completed?
Simulation model.
Simulation model. So he has done the simulation model. We'll finish this waiting line theory, and I think Professor Adakne will conduct inventory control models, and with that, we will be able to finish the unit number 6. I think we have almost completed unit number 5 till 5 we have completed. If there are any concerns, any doubts, any problems, we'll try to solve them later on. But next time we'll go for model number 4. It will take hardly 20 minutes. So on some day we'll conduct a lecture of 20 to 30 minutes and we will try to finish the last model. इसमें अगर आपको किसी को डिफिकल्टी है तो आप मुझे सब पे कन्वे कर सकते हो. I will try to solve those difficulty. With this, we have completed model number 1, 2, and 3. Thank you very much. किसी को difficulty है अभी?
Nice sir, all good.
Any problem? ओके, आई विल सप्लाई दिस पीपीटी। ये जो दोनों पीपीटीज है, लास्ट पीपीटी और ये पीपीटी, मैं आपको आपके व्हाट्सएप ग्रुप पर मेल कर दूंगा, सॉरी सेंड कर दूंगा उसमें। और मीन टाइम में पढ़ना है, समझना है और इसको कंप्लीट करना है, राइट? तो थैंक यू वेरी मच।
सर हेलो
हेलो हेलो, यस।
सर, फाइनल आंसर हमेशा मिनट में ही रखना ना?
नॉट नेसेसरी, यूनिट्स, यूनिट जो है वो सेम रखना है आपको। आप आर में रख सकते हो, मिनट्स में रख सकते हो, लेकिन जब भी आप सॉल्व करोगे तो यूनिट ऑफ टाइम आर में रखना है लैम्डा को, तो म्यू को भी आपको कन्वर्ट करना पड़ेगा अगर वो मिनट में दिया है तो। आखिरी जो लास्ट आंसर है वो आर में हो सकता है या मिनट में भी हो सकता है, इट डिपेंड्स ऑन यू।
ओके सर, थैंक यू।
थैंक यू वेरी मच। हेलो,
हेलो।
हेलो, हाँ बोलिए, नामदेव बोलिए।
सर, आपके पास जो बुक है उसमें और कोई न्यूमेरिकल्स हो गए तो आप उसकी पीपीटी बना के शेयर कर सकते हो क्या?
मैं आपको क्वेश्चंस जो है वो आपको व्हाट्सएप पे भेज दूंगा। सभी जो क्वेश्चंस है उसके सॉल्व अनसॉल्व क्वेश्चंस जो है उसका एक पीपीटी बना के आपको भेज सकता हूँ मैं, ठीक है?
जी सर, बेहतर।
प्लीज रिमाइंड मी, आई विल सेंड, ठीक है? और उसके साथ में आपको 5 साल के पेपर देख लो, दैट विल बी मोर देन सफिशिएंट, ठीक है?
ठीक है सर।
थैंक यू।
सर, ये बुक का नाम कौन सा है आप जिससे पढ़े थे?
मैंने वो एक आईआईटी मद्रास के एक प्रोफेसर है, आईआईटी मद्रास के एक प्रोफेसर है, मिस कलावती, ऑपरेशन रिसर्च बाय मिस कलावती,
ओके सर।
ठीक है? उसी के जो सॉल्व और अनसॉल्व प्रॉब्लम है वो मैं आपको भेज दूंगा, राइट?
ओके सर।
थैंक यू एंड गुड बाय।